expected value for discrete random variables. What's a variable?
Number.
Ooh. It's something about a number, yeah.
The X placeholder for whatever value.
Yeah, and we usually use a letter for it. Could be an X, could be a Y, could be really anything. We often also use like Greek letters and things when we're trying to do variables. In statistics, random variables are different than regular variables. If I'm giving you an algebra problem and I just say like 2x plus 5, that x could literally be anything because I didn't put an equal sign and stick something on the other side. If I said 2x plus 5 equals 10, now that x only equals one thing, you would solve for it. You'd say, yo, Jen, x has to equal this. But if there's no equal sign there and I just say 2x plus 5, you can plug in whatever you want for x. It doesn't even have to be a nice number. You can plug in pi if you wanted. But if it's a random variable in statistics, the variables are certain values that come usually from some kind of experiment. Usually that's where random variables are coming from. And because they're coming from some kind of experiment, they can't take on just any old value. They have to be the possible values for the particular experiment that we're talking about. We already talked about discrete as a vocabulary word versus continuous as a vocabulary word when we talked about quantitative versus qualitative things. When we had discrete and continuous, we were talking about numbers, quantities, and we said it's discrete if it's like 1, 2, 3, like numbers we can actually count, or very specific numbers could still have could still have decimals in there, but they're not like, can't take on just any old value. So like shoe sizes could still be discrete because you could wear a 7 or a 7.5 or an 8, but we're still pretty able to count those. There's not like an infinite number of shoe sizes. You're not going to wear a 7.575 shoe. You might wear 7.5. When we're talking about discrete random variables, we're saying that the variable is going to take on only values that are possible for the experiment, and there's a countable number of them. They can't take on just anything. Later, when you're talking about statistics, different things like our normal distributions and stuff, we're talking about a continuous variable. So they usually start with the discrete random variables, and then we move into continuous things later. So that's kind of an intro there, but let's talk about this experiment thing. We've got an experiment. You've got a fair die. Die is the singular word for dice. So if you're like, what? Why are you saying die? If there's only one of them, we say you have a die. A 6-sided die is fair if when you roll it, you could get a 1 or a 2 or a 3 or a 4 or a 5 or a 6 with an equal amount of probability. There's actually unfair dice. So like if you go to Vegas or whatever, there's like, they've made very special dice that have like special things weighted on each side, because if you actually like hollow out the numbers or actually like put more weight on one of the sides, it might be more likely that you get a particular number to roll. So some people have unfair dice. Fair dice means it's equally likely you would get a 1 or a 2 or a 3 or a 4 or a 5 or a 6. So for this one, our problem says we're rolling a fair die. It's 6-sided. And we're going to let x, which is our random variable. When we make the variable capital in statistics, we're usually talking about a random variable. And so in this case, we're saying our random variable x is going to be the number that appears on the die. So what are the possible numbers that can appear on my die? I already said them, right? Yeah. 1 through 6, right? You can't get a 0. It's not possible. So this is how it's different than a regular variable. A regular variable, x is allowed to be 0, right? But here, x can't be 0, and x can't be 7, because we can't roll a 7 on our 6-sided die. So a random variable takes on only those values that the experiment would allow. Yeah, so the first thing says, let's compute the expected value. Did she talk about expected value yet?
Yeah.
Possibly, possibly not. The expected value when we're talking about these situations is another way of saying the mean. So sometimes you'll look on the formula sheet and it will say mean / expected value. They're asking for the mean of all the things that could happen in this experiment. Okay, so what we would first need to do is figure out what could possibly happen in this experiment. And what could happen in this experiment is that you could roll a 1. So I'm going to write down what my possibilities are for things that can happen. And then I'm going to write down my probabilities of that thing actually happening. So here's my capital X value. It could be that it's just a 1. It could be that it's a 2 or a 3 or a 4 or a 5 or a 6, but that's all that that X could be. So when we're talking about the random variable X, there's only 6 possibilities. Now, the probability of each of these things, if it's a fair die, the probability of rolling a 1 should be 1/6. And the probability of rolling a 2 should also be 1/6. And a 3 should also be 1/6. And a 4 and a 5 and a 6. It's pretty boring. All the probabilities would be 1/6. This is a probability distribution table because it's showing all the possible things that we could have for our random variable, and it's showing all the possible probabilities. And one of the characteristics is if you add up all the probabilities, it always has to add up to 1. So if you added 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6, you'd have 6/6, which would add up to 1. So that's one thing that always has to happen when you've made a probability table like this. Question?
So, when you have like an equation and it goes E of X equals something something.
Yep.
The X is the variables, sorry, the numbers on the side.
Yep, the expected value of the random variable, and it can take on all those things. Yep.
But when you have to do like E of X
Mhm.
or something, you put the probability in.
We're gonna put the probabilities in it. And so I'll show you what the formula says. Our E of X formula, or the expected value formula, is little x. Little x represents each of those values there. So little x means I'll plug in 1 the first time and I'll plug in 2 the second time, all that kind of stuff. Sorry, I didn't actually, don't write the x down yet. Or if you did, leave yourself a tiny bit of space. Jen didn't put the sum sign in front of it. Sorry, here's my sum sign in front of it. There we go. Now little x goes there. And we multiply that times the probability that capital X is equal to that little x. When she gives you a formula sheet for midterm number 2, you'll probably have this formula on there. An expected value will be, you'll take each of the values of big X and we'll put them there. And then this is the probability that big X is equal to each of those little x's. So this is a little x, and that's 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 a little x. Big X means that we're using that to mean the random variable. So me putting that sum sign in front of it says I'm going to take the value of the first thing and I'm going to multiply it times its probability. Then I'm going to add the second thing times its probability. Then I'm going to add the third thing times its probability. Then I'm going to add, so we're going to add 6 things together. So I'm going to write that all out now. This is equal to
1 times 1/6 plus 2 times 1/6 plus 3 times 1/6 plus 4 times 1/6. Almost done. Plus 5 times 1/6 plus 6 times 1/6. So all I did is I took each of the values of the random variable, multiplied it by its corresponding probability. In this case, the corresponding probability was the same for all of them. That isn't always the case, but we started with one where they are. So now we're going to add these all up. So 1 times 1/6 is just 1/6. This is going to be 2/6. This is going to be 3/6. 4/6. 5/6. And 6/6. If you're getting nervous because you're like, Jen, this is going to be more than 1. Yes, an expected value is not the same thing as a probability. If I was asking you for a probability, the biggest number I can get is 1. But if I'm asking you for the expected value, I'm allowed to get bigger than 1. We're going to get bigger than 1 this time. Remember with fractions, if you have the same denominator, you just leave that denominator alone when you're adding them, and we add the numerators together. So 3 plus 3 more is 6. Plus 4 is 10, plus 5 is 15, plus 6 is 21. So I got 21 in the top and 6 in the bottom. And if I write that as a decimal, that's 3.5. So my expected value for this experiment, E of X, is going to be 3.5. What does that mean in this case? It doesn't really have a nice physical meaning here where we'd say, if I were to run through this whole experiment, my expected value would be 3.5. And you'd go, well, that's crazy because if you roll dice, you can't get a 3.5. You can get a 3 or you can get a 4. That's okay. In this case, what they're saying is if you went through all of them, the probability of you doing this full experiment and then adding up each of them, the sums of them, we're going to get an expected value of 3.5. It's okay that it doesn't actually match up with a thing in the real world. Sometimes the experiments make a little bit more sense in the real world. So we'll see some like that later. But for this one, it's okay that we got a number I can't actually roll. What this is saying is that after we've done this experiment, we've got a kind of, again, expected value is another way of talking about a mean here. So the average of all of the things that could happen in this is also called a mean. Or the symbol for the mean, the mu for this experiment. So she could on a formula sheet write the expected value, or she could say the mean, and it would mean the same thing. I say that because the next thing is asking us to compute a variance for the X. Now we have a formula here for the variance. It says the variance of our random variable X is equal to the expected value of X squared minus the expected value of X in brackets, squaring that answer. We've actually already calculated one of these numbers, and we haven't calculated the other number. We have not calculated this yet. When we did the expected value, we did the expected value of just X without it being squared. So over here, what we've calculated already is that number right there. And so all we would have to do is square that number. So right here, that number is 3.5. So in our formula, we'll take 3.5 and we'll square it. But we actually have to go calculate this number. We don't have that one yet. So we have a separate thing we have to calculate. When we do this squared, what you're doing is you're taking the numbers in this column right here and you're going to square them. So you're going to do 1 squared times 1/6, 2 squared times 1/6, 3 squared times 1/6, and so on. So we're just gonna square the x value. So to calculate the e of x squared, that's just 1 squared times 1/6 plus 2 squared times 1/6 plus 3 squared times 1/6 plus 4 squared times 1/6. We're almost done. Plus 5 squared times 1/6 and plus 6 squared times 1/6. So what's that going to come out to be? 1 squared is just 1 times 1/6. 2 squared is 4 times 1/6, so that'll be 4/6. This will be 9 times 1/6. This will be 16 times 1/6. 25 times 1/6 and 36 times 1/6. Again, we would just keep the 6 in the bottom and we're going to add up all the top numbers. I already added them up previously. They add up to 91. So we get 91 over 6. Is that the answer? No. That was just this part of the formula right there. We were calculating that part separately. So we've got that number right there. That's 91 over 6. And then we're going to do minus this number squared. So now my variance of x is equal to that 91 over 6 minus that e to the x that we calculated in part 1, which was 3.5 squared. And that's going to come out to be approximately 2.92. I don't have it on there, but if I asked you for the standard deviation, what would you do now? You would take the square root and you would be done. Good. So if you have the variance of things, the definition of the standard deviation is the square root of the variance. So if you just went ahead and put a square root over that, you'd have the standard deviation. I didn't ask you for that, but if I did, you could do it. You just have to square root it. So I know at the moment you're probably like, what are we doing? None of this seems particularly interesting. I know. I just want to show you how these calculations work because you're going to have some homework problems where you're doing exactly this. You'll have something to kind of look back on. I'm going to do another one that kind of looks like at least one of the homework problems I remember her giving in the past. I don't know what homework problems you're going to get this time, but let's do another one. This is like a gambling type of problem. Variance part. Okay, this one says, a fair coin is tossed. And you're probably like, what's a fair coin? There actually are coins where it's more likely you're going to get heads than it is that you're going to get tails or vice versa. But a fair coin means it's equally likely you're going to get heads or tails. So if a fair coin is tossed, you win 3 points if heads appears, but you win 7 points if tails appears. Let y be the number of points you win. So we want to compute the expected value for this experiment. And we're just reminding you each outcome has a probability of 1/2 because it's a fair coin. Okay. So for this particular experiment, only 2 things can happen when you flip this coin. You're either going to get heads or you're going to get tails. if you get heads, the only value that we could get for our y is 3. And if you get tails, the only value we could get for our y is 7. So the two numbers that our variable is allowed to be are 3 or 7. So remember, a regular variable, you can plug in whatever the heck you want, but for a random variable, it's only what are the outcomes of the experiment. So for this one, the outcomes of the experiment, it's either 3 or it's 7. There's nothing else it can be. So what we would have here under my y is 3 or 7. For probability, because it's a fair coin, it's 50-50 or 1/2 and 1/2. That won't always be the case that they're exactly the same. We'll do one soon that's different. So the question says, compute the expected value of y. Okay. Expected value of y, E of y. What it wants you to do is take this first number here and multiply it by its probability. So 3 times 1/2. And then add this number right here and multiply it times its probability. So we only have 2 numbers we got to do on this one. We had 6 on the last one, but this one's a lot shorter. So this would be 3/2 plus 7/2, which comes out to be 10/2, which comes out to be the nice number 5. Okay, so I told you in our last example, the expected value we got was a 3.5, and it didn't really mean anything for that particular problem because on your dice, when you roll dice, you can't get a 3.5. You can get a 3. You can get a 4, but you can't get 3.5. In this case, the expected value has a more like physical meaning to it. It's saying if you kept playing this game over and over and over again, I would expect that you would get 5 points on average when you're playing this game. Okay. Does that mean that every time you play the game, you're going to get 5 points? No, we're saying that if you were to repeat this experiment over and over and over again, the average of all of the times that you did it, you should average 5 points when you do it. And so that's where, when they call this expected value a mean, they're averaging, if you were to do this experiment 100 times or 1,000 times, what would be the average of all the points you would get if you played it that many times. But each individual time you do it, it totally depends. Like, you could just keep getting heads over and over again, or you could just keep getting tails over and over again. But if we were to average together all of the times that you did the experiment, you did it a bunch of times, we would expect that the number of points you would get would be 5. Does that seem weird? I still think it's a little weird because you win 3 points if you get heads and 7 points if you get tails. You never actually win 5 points. So how is the average of all the things that you're getting a 5? Still feels weird. Like, it still doesn't feel like that number makes any sense. But ultimately, because it's an average, it's the same sort of way like if we were talking about the average of all the incomes of all the people in the room, that the number that's the average doesn't necessarily match up with any of you in here. So if we were like, well, the average salary of students in here is $27, and you're like, yeah, but literally no one in here makes $27. It just means that somebody in this room makes a lot more. And then other people are making, 17, 18 bucks an hour, and then the average comes out to be 27. So in the same way that none of the numbers that are actually possibilities, 3 or 7, isn't our average here, that's okay that it's not coming out to be one of those. Again, with computing the variance, it's the same formula we used last time. So I'm going to write the formula and I want you to see if you can do it for this one. So your formula when you do this for the variance of y is going to be the expected value of y squared minus, in brackets, the expected value of y. On the outside of that, you're squaring that number. So there's the formula. See if you can do that. I promise I'll do it in just a minute, but I want you to see if you can do it. I guess I could drop it back down so you can see what you got for expected value of y. You already got one of the numbers that you need up there. It's 5. Before. So what we had to do is take each of the y values that we had and square them. The 2 y values that we had were 3 and 7. So we squared the 3 right here, and we squared the 7 right here, but we still just multiply them by the 1/2. So this one becomes 9/2, and this one becomes 49/2. When we add those together, they actually come out to be 29. So that's the first part of the formula right here. This number right here is the 29 minus this number right here inside the brackets is that 5 that we got up in this step. So we're going to do 5 squared. So we do 29 minus the 5 squared. So 29 minus 25 gives us the 4. And again, if I asked you what's the standard deviation for this, you'd say square root of 4, which is 2. Good job. Okay. So I've been having you write out the probability distributions for these experiments. They've been pretty boring so far. Usually probability distributions have a little bit more going on. So my next page, we have a more involved probability distribution. This time our experiment involves us rolling 2 fair dice. And we're going to add up the dots when we do it. The expected value for a thing is going to be a little bit more complicated because the actual distribution we're going to take is a little more complicated. So it says 2 fair dice are rolled. Let X, which is our random variable, be the sum of the dots on both dice when you roll them. Okay. So this time, if I ask you what's X allowed to be, so we're going to write out our X's and our probabilities. Okay, if I roll 2 dice, what's the smallest thing that I could get? 2. Because if I roll both dice, the smallest thing I can get on one of them is a 1, and the smallest thing I can get on the other one is a 1. But because the random variable is the sum of the dots, the smallest sum that I can get is 2, because I got 1 on this one and 1 on this one. So 2 is actually the smallest X value that I can get. Could I get a 3? Yeah, because I could get 2 on one of the dice and 1 on the other dice, or vice versa, right? So I could also get a 3. Could you get a 4? Yep, because we did a 2 and a 2. And I could get a 5 because I could get a 3 and a 2. I could also get a 4 and a 1, right? So there's other ways we could get a 5. So we'll have to keep that in mind when we do the probabilities, but we're not there yet, okay? I could get a 6 if I had a 3 and a 3, or a 5 and a 1, or a 2 and a 4. There's lots of ways I could get a 6. Okay, I could get a 7 and an 8 and a 9 and a 10. When do I have to stop? 12. And the reason it's 12 is that the highest thing I can get on one of the dice is 6, and the highest thing I can get on the other dice is 6. So 12 would be the biggest number. So again, a random variable is different than a regular variable, because if I'm just giving you a variable in algebra, a variable could be any number. But in this problem, my random variable, it can't be 0 or 1, but it can be 2. And it can't be 13. Like, there's very specific values it's allowed to be. So random variables can only take on whatever the experiment allows. Okay. Now we need probabilities, and that's going to be a little bit trickier here. Okay. In order to get 2, when I roll the dice, there's actually only one combination that's going to give me 2. But when I roll the dice, there's 6 things that could happen on this die over here. 1, 2, 3, 4, 5, or 6. And there's 6 things that could happen on this die over here. So the actual, like, total number of things that could happen follows the multiplication rule. It's 6 times that 6. There's 36 possible things that could happen. So out of those 36 possible things, there's only one way I can get those dice to add up to 2. And that's if I get a 1 and a 1. So the probability that I get a 2 is 1 out of 36. And I probably should have like not written the numbers so close together, because I'm gonna need to make those fractions tinier when I write them over here. But in order to get a 3, I could get a 2 and a 1, but I also could get a 1 on this die and a 2 on this die. So there's actually 2 ways that I could get a 3. So I have 2 out of 36 ways that I could get a 3. For a 4, I could get a 2 and a 2, but I could also get a 1 and a 3, or I could get a 3 and a 1. So there's 3 ways that I could get a 4. I won't make you survive all of me listing all of them out. Will you trust me that I counted the other ones correctly as we go? Okay, so the number of ways that you can get a 5 is 4 out of 36. The number of ways you can get a 6 is 5 out of 36. The number of ways you can get a 7 is 6 out of 36. For an 8, it drops down to 5 out of 36. For a 9, it drops down to 4 out of 36. For 10, now we're at 3 out of 36. For 11, it's 2 out of 36. And at 12, again, the only way we can get a 12 is if we get a 6 and a 6. So there's 1 out of 36. So it's kind of symmetric, not kind of symmetric, it is symmetric. We started with a 1, we went up to 2, 3, 4, 5, 6, and then it peaked And then it went back down again to 5, 4, 3, 2, and 1. So this probability distribution is a little more complicated than the other ones we did. The other ones, it was the same number, but it doesn't have to be the same number. But to do the expected value is the same formula. The expected value is this times this plus this times this plus this times this plus this times this and so on. So we have to take all of them, multiply them by its corresponding probability and add them all up. So I'm going to write it all down, but I already did the calculation, so it won't be so terrible. So my expected value is 2 times 1 over 36 plus 3 times 1 over 36 plus 4 times, oh, not 1, sorry, I meant a 2. I'm already messing up. There we go. 4 times 3 out of 36. 5 times 4 over 36. 6 times 5 over 36. 7 times 6 over 36. So I'm going to pause for a second. The most likely number when you do this is for you to get 7, because there's 6 different ways you could get a 7. But then after that, it's less likely to get any of the other things. So 8 times 5 over 36. 9 times 4. 10 times 3. 11 times 2. And 12 times 1 over 36. Okay, I promise if you go through and don't mess up anything, this comes out to be 7. The nice whole number 7. And I actually totally did the step 2 up there. Sorry, you guys are probably reading the handout better than I was reading it. You're like, why'd you do that? And then, yeah, okay, sorry. The expected value calculation I just did is this one right here. That's kind of good. It fits there. So another way she could write this is what's the average value that comes out when you do this experiment. So another way of saying the expected value is the average or the mean value. She could ask for the mu. And if she asks for the mu, you'll still say 7. It's the same answer. It's a different way she could ask for it. So I said this once before, but I'm going to say it again. When you've got the random variable and then its corresponding sets of probabilities, this probability distribution right here, if you add them all up, they always add up to 1. They have to. That's important for us to do the next page, because if we don't know that, then you can get stuck. We did experiments to get our probability distributions for the first several, but this one says we've got an actual scenario here. People are renting video games. I don't know if that's a thing anymore, but I'm old. So back in the day, people would go into a store and they had to actually like physically rent things. Video games stuck around longer as a rental thing than videos, but they used to have video stores, guys. You couldn't go on anything. There was no such thing as Netflix. If we wanted to see a movie, you had to go into this place and they had cassette tapes. And you'd get home and you'd be so mad because the last person didn't rewind the cassette tape. So like you go to play it, it's halfway through the movie, and you're like, what? It's crazy. But they just spoiled half the fun. Yeah. But video games, people rented for a lot. Well, I don't know, do we still like GameStop? Can you still rent video games? Okay, it's still a thing. Often people rent more than one at a time. True. Hardly anyone went into the video store and walked out with one video. I'm gonna guess same thing with video games. The probability distribution of video game rentals per customer at a particular rental store is given below. So this is at a particular store. This wouldn't apply to all video game stores, but here's one particular video game store. They're saying that the probability that somebody walks into that store and rents video games is only 3%. So most people going into the store are renting something. Only 3% of them are not renting anything. Okay? Half of the people who go into this store are renting one video game. 24% of the people are renting 2 video games. We don't have the number for the number of people who are renting 3 video games. 4 video games, 7% of people are coming out with 4. And 4% of people are coming out with 5. So one of the first things we need to be able to figure out is how many people rented 3. Can you do it? What's the trick?
Add up all of the minus and then take away from one.
Yeah. So what we were saying in the last several examples was that the probabilities always have to add up to 1. So even though I didn't give you this one, you can figure it out. If you add up the remaining ones and you subtract them from 1, you'll find out what that one's supposed to be. So if we add up all the other ones, I'll be lazy. I'll use a calculator. We got 3% plus 50% plus 24% plus 7% plus 4 more percent. That came out to be 88%. So I got to do 1 minus 88%. What's that going to give me? 12%. Nicely done. So I'm going to write 0.12 here because all of these things, I'm going to write a little note off to the side. They all have to add up to 1. And that's always the case when we have these probability distributions. So some of your homework problems, that will be the thing. You'll have these like charts and numbers will be missing. And you got to know, oh, if it's probabilities, they always add up to 1. Okay. So we just got the answer to part A. It says find the probability that a customer rents 3 video games. There's a 12% probability that a customer rents 3 video games. Question.
I would write that probability. E of X is equal to 0.
Yeah, good question. If I wanted to write the probability that they rent 3 video games, that would be probability that capital X is equal to 3 is equal to 0.12. Perfect. Good question. So that capital X is just saying the probability that the random variable is equal to, and then normally if they don't write the number, they write lowercase x as the next thing. It's just super weird, but the lowercase x just means the actual number. In this case, because we have a specific actual number, we replace the lowercase x with the number itself. And when we talk about probabilities in that format, we write it as a decimal instead of the percent. But when you're writing a sentence about it, either one is fine. When we talk about things in the real world, you're like, what's the probability something's going to happen? We usually like to talk in percentages. We like to say it's a 50% chance it's going to happen rather than say it's a 0.5 probability. People are like, It means the same thing. I don't know why we're more comfortable out loud saying percentages, but we just tend to be a little different with English than we are with the math. Okay. Find the probability that a customer rents, this is important, at least 4 video games. The next few sections, those types of words matter a ton. At least. At least, does that include 4? Yes. So when it says at least 4 video games, I'm going to count up 4 video games and 5 video games. So both of those are going to get added together. So probability that they rent at least 4 video games would be the 0.07 plus 0.04, which is going to give you 11. So you have a 11% probability. That a customer rents at least 4 video games. Part C says, find the probability that a customer rents at most 2 video games. Okay. At most 2? Does that include 2? Yeah, it still includes the 2. So at most means that they could rent 0, or they could rent 1, or they could rent 2. So we're going to add up the 3 and the 50 and the 24. I'm going to add all of those up. Pretty likely, 77% chance. And I said chance this time, but I should have probably written 77% probability. It's okay. They mean the same thing, but I was using the probability language before. On average, how many video games do you expect customers to rent at this store? What am I asking you for here? I'm asking for the mean, which is another fancy way of saying the expected value. So it's what you've been doing, but this is another way she could ask you this type of question. So what do we have to do? We have to take this times this, plus this times this, plus this times this. So that's always going to be how these go. So we're going to put all those together. Expected value. 0 times 0.03 plus 1 times 0.50 plus 2 times 0.24 plus 3 times 0.12 plus 4 times 0.07 and plus 5 times 0.04. I didn't pre-add this up, so I got to do it. Got 1.81. So on average, we expect customers to rent 1.81 video games. That doesn't mean anything exactly, right? Because you can't walk out with 1.81 video games, but it means on average, they're going to rent 1 to 2, right? Okay. So the next thing that normally pops up is one of two things. So I haven't seen your guys' notes yet. So somebody, when you have a chance, go in and upload more notes for me in discussion, and I promise I will read through them. But the next thing that you'll tend to talk about is either uniform distributions or binomial distributions. Have you talked about either of those yet?
Not sure.
She might have talked about a binomial distribution. Did she talk about this really cool symbol called the factorial? There's a real good chance she hasn't yet, but there's this symbol that you know of in English. When I draw this symbol in English, you say, that's an exclamation point, Jen. In math, it's not an exclamation point. It's called a factorial. Anybody seen this before in math? It has a really interesting use. So if I write 5 with an exclamation point after it and it's a math class, I'm not saying 5, like yelling it or anything like that. This means 5 factorial, and it means 5 times 4 times 3 times 2 times 1. If I write 2 factorial, this just means 2 times 1. If I write 10 factorial, it means 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So why does this exist? Because mathematicians are lazy by nature, and we wanted a shortcut so we wouldn't have to write all those things out all the time. So if it was something where we needed all the numbers like that, we were like, cool, I'm just going to make some cool notation. So that's called a factorial symbol. When we get into the binomial distribution stuff, understanding how to work with the factorials is big. So you'll have some things where you'll have factorials in the top and factorials in the bottom. So for instance, I could ask you to do a calculation where I want you to simplify 6 factorial over 3 factorial. And so when I write that, I'm writing a fraction for you. And instead of you multiplying out 6 times 5 times 4 times 3 times 2 times 1, and then 3 times 2 times 1, what you would recognize is that 6 factorial is 6 times 5 times 4. And then if I were to write the next several things, wouldn't that be the same thing as 3 factorial? Because the next several things I would write would be 3 times 2 times 1, but that's the same thing as the 3 factorial that's in the bottom. And so now we can use our little shortcut of, if you have the same thing in the numerator and denominator of a fraction, we can go ahead and cancel them out. So the answer to 6 factorial divided by 3 factorial is just 6 times 5 times 4. 6 times 5 is 30, and 30 times 4 should be 120. So we didn't actually need a calculator on that one. Yay! We can shortcut things. normally we'll have multiple things in the bottom. So we could have something like 6 factorial and then 3 factorial times 2 factorial in the bottom. Okay. So again, I would start by going 6 times 5 times 4, and then I'd go, ooh, well, I already see a 3 factorial, so I'm going to use my shortcut here and not finish out writing out 3 times 2 times 1 because I've got that 3 factorial in the bottom. But then I also have a 2 factorial here, which is just 2 times 1. So these parts can cancel. And in the top, I have 6 times 5 times 4, and in the bottom, I still have 2 times 1. You're allowed to do your 120 now and divide it by 2 if you want. Or you could say, ooh, 2 goes into 4 evenly, or 2 goes into 6 evenly. You could do some more canceling if you wanted. You could say 2 goes into 2 one time, and 2 goes into 4 2 times. And now the top is 6 times 5 times 2. And in the bottom, you have 1 times 1, so we don't even care about the bottom anymore. So this would be 30 times 2, which is 60. Or if you had done the top and got 120 and the bottom and got 2, 120 divided by 2 still would have given you that 60. So when she goes to talk about the binomial theorem stuff, we're going to have some calculations that involve those factorial things in there. They're not terrible, but if you've never seen one before, you can be like, why is she writing a bunch of exclamation points in math? It's not an exclamation point in math. It's called a factorial symbol. Binomial distributions. The word binomial has the prefix bi in it. So like with a bicycle, that's 2 wheels. Binomial, we've got 2 terms. And when we're talking about a binomial distribution, what we're saying is only 2 things could happen in a particular experiment. So when we were doing our dice probabilities, that one's not binomial because you could get, when you're rolling dice, you could have many, many different things, not just 2 different things. But when we were doing the coin flip problem, and we said that there were only 2 things that could happen, you could either get a heads or you could get a tails. That one would be a binomial distribution because there's only 2 outcomes for the particular experiment. But in the real world, there's lots of different things that we could consider a binomial distribution with 2 outcomes, meaning either this thing happens or a different thing happens. And if you don't really care what the other thing is, so you could have a poll where you're asking people political party preferences. There's more than 2, right? But when you do the survey, you could say, I polled people to find out if they were Democrat or not. Even though there's other things they could have been besides Republican, there were other choices there. They could have been independent, Green Party, all the other different things. But if the way that you asked the question in the experiment was, are they Democratic or not? Now it's a binomial. Or if you're tallying people shooting baskets into a basketball hoop, there's lots of things that could happen. But if you're just asking, did the ball go in or did it not go in? It's a hit or a miss. So when we talk about binomial distributions, often they'll use the words, the probability of a success and the probability of a failure when they're talking about the binomial thing. And success and failure doesn't actually mean like a good thing and a bad thing. Really, truly, like a lot of the times when we're talking about binomial distribution stuff, we could be talking about terrible things like the probability you have cancer or not cancer. But when they're talking about that particular problem, the probability of a success is the probability you have cancer. So the success isn't a great thing. And not having cancer is considered the fail in most of the situations when we're doing those types of problems. It's not that not having it's a bad thing. It's just the way that they label it, that if it happens, we call that a success. If it doesn't happen, we call it a failure. So that's going to probably be, if she doesn't talk about uniform distribution, then binomial distribution is probably her next topic. Yeah.
Base theorem, which I believe is something like you have to the side of handout and on the back. Please give it a history, or at that point, but I believe she did probably history. I'm not sure if this is her first time.
How are you feeling about Bayes' theorem? I think I still have that handout. Let me check. I might not have come prepared. I think I gave that last handout to somebody in office hours. I will come prepared next time with it so that we can go over it. Sorry about that. Will you hate me if I end a few minutes early today? Not at all, Jen. Okay, I'll stand up here and ask questions, answer questions if people have them. Otherwise, I'll see you on Thursday.